Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is the second law for reacting systems, and the sections in the textbook are 15.6 to 15.7. So here are the three learning outcomes. At the end of this, you'll know the appropriate energy balance for a reaction system. You'll be able to quantify an absolute entropy for an ideal gas component, and you'll be able to calculate the entropy generated and the exergy destroyed in the combustion process. So let's talk about the entropy balance. And we've seen an entropy balance back in Chapter 7 of Basic Thermodynamics, but now what we have is a reacting system. And so let's imagine here I have a hydrocarbon fuel coming in one pipe, and I have, say, oxygen and nitrogen, which would be a mixture of air coming in a second pipe. And we'll go ahead and just say that this comes in about room temperature, which would be about 25 degrees Celsius, and atmospheric pressure, so about 101 kPa. And we'll have this coming out at 101 kPa as well. So some sort of a constant pressure combustion process. And what we're looking at here is where is entropy being generated? And it's actually being generated in a couple areas. So first of all, if you remember from Chapter 13, when we mix two gases, we generate entropy. So as the hydrocarbon fuel and the oxygen mix, we're actually going to be generating some entropy right there. And then when it goes ahead and burns, you might wonder, does that generate entropy? And well, it definitely does, because it's a very irreversible process. You can't take these combustion products and ever get the reactants from it. So that's very, very irreversible. So you're going to get entropy generation at that point, and then those material will leave, and usually it's at some sort of higher temperature, which would be representative of a higher entropy. We may be losing some heat if this is a combustor that's heating something. That right there will remove some entropy from this system. So let's look at our overall entropy balance of what it looks like. Now, if we look at what happens is we have our entropy going in, so this is the entropy of the reactants going in, and then whatever that entropy is, we have the generation, and it generates both by mixing and by combusting, so both of those two processes are going to contribute to the S generation, and that's going to be equal to the products. And then over here on this term, I've got Q over T naught, which is the amount of heat that leaves over T0. And I have it on the right-hand side. You could think of it as subtracting, because as we lose heat from the system, entropy is going to decrease of that. Or this is an entropy generation, or not entropy generation, it's an entropy transfer at the output. All right? So there's my overall entropy balance, and that's what we're going to be working with here. And we'll delve a little bit more into the details of it. If this is a steady flow system, the entropy of the reactants, we would think of it as the mass flow rate of the reactants times their specific entropy. And usually what you're going to end up doing is summing over all of your reactants, because we'll take each one as an individual component. We're going to have a rate at which entropy is being generated, and then that's going to be the mass flow rate of the products. Again, usually you'll go ahead and sum over each one of the individual products, the CO2, the water, and the nitrogen, for example. And then this would be the rate of heat transfer that's leaving over T naught, and T naught would be the temperature at which the heat is going out. So if the combustor was at, say, 500 degrees Celsius, but the room was at 25 degrees Celsius, we'd be using this 25C. You want to convert it into Kelvin in that equation, so it would be 298 Kelvin. The reason we care about the amount of entropy being generated is more because we want to know the exergy being destroyed. And so remember, exergy destroyed is the entropy generated over T naught, or in a rate term, we could go ahead and say this is the rate at which exergy is being destroyed. And so what we're going to do today is we're going to find out how much exergy actually gets destroyed by burning something. And we're going to find out it's fairly significant. Right. So one of the things we need to do is we need to determine an absolute entropy. And the reason is we're trying to find these values of S. Remember, we're normally going to sum over all of my reactants. And so we're going to need to find entropy of reactants. But over here, we have our entropy of our products, which are different. So similar to like we had in enthalpy, we sort of need an absolute value, because over here we're going to have things like, say, oxygen, which is one of the reactants, or maybe CH4, which would be methane. But over here we're going to have CO2, we're going to have water, and those are going to be different. So we don't have just simply a change in entropy from inlet to outlet. This completely gets consumed, and this gets generated. So we need an absolute value. We saw a similar thing when we were doing enthalpies. And this is what we'll do in order to determine that. Remember this equation back from Chapter 7, which has allowed us to find a change in entropy This was of an ideal gas, and it would integrate between two temperatures of Cp dt over T, and then minus R ln of P2 over P1. And so this arises because it was an ideal gas. We have this term right over here. And we'll stick with everything that's an ideal gas for this chapter, so we'll be using this equation. And what we want to do is we want to determine the absolute entropy, which means we want to integrate from a point at which it's 0 up to its final state. And so that brings us to something called the third law of thermodynamics. And you don't run into the third law very often, but the third law states in words is that if I was to go down and form a perfect crystal at 0 degrees Kelvin, we can go ahead and say the entropy of that is 0, meaning it can't get any more order. That's the lowest entropy that it can have. This is what the third law says, and we don't really use it all that often, so you don't run into it much, but there is a third law of thermodynamics. And so what that means now, if we come back to our gases, if I was to go and integrate from 0 Kelvin up to some temperature T, I could go ahead and then determine what the entropy is, because the entropy at 0 Kelvin was 0. And one of the things is this entropy is 0 at 0 Kelvin and atmospheric pressure, which is called P naught, which would be like a 101 kPa, for example. And so what we'll do now is we're going to integrate from whatever pressure we want, starting over at P naught, which is going to be atmospheric pressure. Right? So what that ends up saying is that here's what my absolute entropy value is. This value of S is going to appear into that equation up there is S0, and the reason we're going to do this S0 value, remember this from chapter 7, these are temperature-dependent heat capacities. We're starting out at 0 Kelvin and often going up pretty high temperatures, hundreds of thousands of degrees. And so we need this S superscript 0 value. It's called the standard state entropy, because that right there is only a function of temperature, and it's at atmospheric pressure. And then this right over here, P naught, is atmospheric pressure, and this is the actual pressure that we're at. So what we're doing is we're finding the entropy at any arbitrary temperature and pressure by finding the standard state entropy at that temperature and then including this pressure term right over on the right-hand side there. All right. So let's try to remember where we get those values. So first of all, the S0 value, here's table A20. You can get them from all these ideal gas tables. This is for carbon dioxide. And so it's the last column right over here. This is S superscript 0. And notice that the units are kilojoules per kilomole. It's pretty helpful because normally we're looking at reacting systems and we're going to want it per kilomole. So we can go ahead and just pull that value off and we just return to the previous slide and just remind you that's this first value I have. And then I need to go ahead and add the second term to it. So that just gives me the first term that I have. If you're using EES, you can get these S0 values by using the entropy function and setting your pressure to atmospheric pressure. So here I've set my unit system to SI, so my pressure would be 101.3, and that's going to go ahead and give me my S0 value at any arbitrary temperature. So for example, here I have it at 600. So this function right here would give me 243.199. Okay. Now let me just jump back one step again. Remember, that just gives me the S0 value. Then I would need to add this component. You can actually make EES do that for you as well. And that was what you can do to go ahead and get that second term right there is just go ahead and give it the actual pressure you're at. And so this 500 is this pressure right here. And this is going to give you the total entropy. So similar to like when we were dealing with entropy values, you don't necessarily need to have EES give you the two components. So when you do those two components and you're looking it up off the table, you want to use EES, just go ahead and ask for your entropy at your temperature and pressure that you're doing. Hydrocarbons. Since we don't have tables of ideal gases, you can get that from A26, which was where our enthalpies of formation were, which was those terms. Here's your standard state entropy again. So remember, standard state here means I'm at 1 atmospheric pressure. This whole table is at 25, so you only have it at 1 temperature for various hydrocarbons. I've cut the table off with more hydrocarbons as I go down. And if you're using EES, you're going to want to use the entropy function again, give it the temperature 298, give it the atmospheric pressure to give you a standard state entropy, and that's going to go ahead and give you S0 for any of your hydrocarbons. So here I do it for ethane. So this is how you can go ahead and get the values from A26 using EES. All right, so here's the example that we're going to do. We kind of looked at this problem before. We were burning propane, and we looked at the amount of heat being given off when we had our combustion product coming out at 300 C, and they went in, if you remember, T in was, I believe, 25 degrees Celsius in that problem. So we'll go ahead and stick with the numbers we had there. We calculated Q for that problem. And what we want to do is go ahead and calculate what the rate of exergy destruction is, which means we need to know the rate of entropy generation. So here's my equation again. I'm going to be first find Sgen, which means I need to find all the individual specific entropy values from our reactants and my products. Q dot we went ahead and got from our previous problem in the previous video, so we can go ahead and just use that value. So let's go ahead and go through this. So what we need to do is first go ahead and find the entropy of all my reactants. And so what I have is I've got propane coming in. Let's just go ahead and write our balanced equation. I have C3H8 plus O2 plus 3.76 N2. It's my air. I'm going to go ahead and balance this equation here in a second. Complete combustion is CO2, water, and nitrogen. And if I go ahead and balance that, I have 3 carbons there. I have 4 waters there. I have 5 water, or 5 in terms front of the air. This is theoretical air. That's going to give me 18.8 in terms of the nitrogen. So there's my balanced equation. And so what we'll do is instead of using mass flow rates, we'll go ahead and just use per mole. So we'll calculate the whole thing per mole of propane that we burn, similar to what we did when we calculated our value of Q. Let's go ahead and find the entropy of propane. So I'll call it S sub P. That's going to be S0. And remember there's this minus R ln of P over P naught. And this is the universal gas constant because we're doing this per mole. So that's kind of convenient. And if we do that at atmospheric pressure, which we have that coming in, that whole term is going to be 0. So I just need S0. I can pull that off the table, A26. And that's going to be 269.91. So there's one of my reactants. My other 2 reactions, I've got oxygen and nitrogen. So let's do our O2. And so again, it's going to have a similar equation. I've got S0 minus RU ln of P over P naught. All right. And so I can get my S0 value at 25 degrees Celsius at 298 Kelvin. That's 205.033. And then minus 8.314. And now the natural log term, the pressure, this is the partial pressure. So I've got air and nitrogen. And so that's going to end up being equal to the natural log of 0.21 P naught over P naught. So essentially the natural log of the mole fraction value. So whenever you have mixtures, remember we've got a partial pressure. Remember the mixing of gases. So I can go ahead and put in my mole fraction there. And this comes out to be 218.3. So I'm going to do a similar thing for N2. The mole fraction here, I'll just write out the second term, so minus RU ln of 0.79 for N2. And that value ends up, I'll skip the intermediate, that's 193.4. And you can verify that on your own. So those are my 3 reactants. And you're multiplying that by the number of moles. I got a 1 in front of the propane, and then I've got a 5 in front of the oxygen, and 18.8 in front of N2. So now what we want to do is we want to do our products. So for example, one of our products would be CO2, so S of CO2, right? And that's going to end up being S0 minus Rn, and then my natural log. And so let's think about this. What is our partial pressure going to be? Well, what we've got is we've got 3 moles of CO2 over a total of 3 plus 4 plus 18.8. And so that's going to end up being the natural log of 3 over 25.8. Again, 25.8 is 3 plus 4 plus 18.8. So that's my mole fraction of the value for CO2. And that comes out to be 236.1. Right? So now I could do the similar things for water. Water is going to have a different mole fraction. It's going to be 4 over 25.8. And then I'm going to have one for the nitrogen at the outlet, which is going to have the natural log of 18.8 over 25.8. So I won't go ahead and write down those values at this point. Again, I can let you do that on your own. But what we want to do now is do our entropy balance. Let me just go ahead and write that out. What we're going to do is we're going to have 3. We're going to do our products minus our reactants. So I have 3 for CO2. The value for CO2 is 236.1. I'm going to add the water, and that is 4. And the value for water, okay, I skipped, was 228.4. And then I'm going to add my nitrogen at the outlet, so 18.8, and that's 214.7. And then I'm going to do subtract out my reactants, and so I'm going to go ahead and subtract my, from the propane value I had 269.91. I need to subtract my 5 oxygens, 218.3, and then I'm going to need to subtract my 18.8 nitrogens at the inlet, and that was 193.4. Alright. And then the last thing I need to do is I need to add my heat generation, and so I'm going to add over here, if you remember from the previous video, that's 1.8 e to the 6th over T naught, and we'll go ahead and call it T naught 298 Kelvin. And so then that's going to tell me what my total entropy generated is. So S generated per mole of propane being burned is 6302. So it's going to be kilojoules per Kelvin K mole of propane, C3H8. And now the last thing we can do is find out what our exergy destroyed is, and what that is going to be T naught times S generated. And so I'm multiplying T naught, and so I'm going to end up with a value of about 2.0 e to the 6, so 2 million kilojoules per kilomole of propane burned, C3H8. Okay? So a pretty substantial amount, right? That's a lot, 2 million kilojoules. Now a kilomole of propane generates a lot of power, but a lot gets burned. And what that is representative of is how irreversible combustion products are. They're very useful, they burn very quickly, they burn very hot, but we actually generate a whole lot of exergy, or destroy a whole lot of exergy when we do it. And in fact, if you read the special section in the book, you'll see that fuel cells are kind of nice because they destroy a whole lot less exergy because we don't go through the combustion process.